Today we're gonna this lecture 28, and we're gonna discuss the Schwinger oscillator model of angular momentum. This is the last lecture of the part that's about angular momentum. So let me start with a review of what we discussed in the last lecture, which was the formal theory of addition of angular momentum. So we said that if you have two different angular momentum, two different degrees of freedom, this could be two spinors, it could be orbital angular momentum and spin angular momentum, J1 and J2. Then we define a total angular momentum, which is J1 tensor identity plus 1 tensor J2. So this is the setup where the total Hilbert space is H1 tensor H2. And if this has J1 spin, this Hilbert space is 2J1 plus 1 dimensional, H2 is 2J2 plus 1 dimensional. The commutation relations are as follows. So of course, operators here support on 1. They will satisfy a copy of SU2. Operators satisfy sitting on the insert on the second tensor factor satisfy SU2 algebra, and the guys on the 1 and 2, they commute with each other. If there are any questions along the way, just to ask. So the story got interesting when we noticed that there are two sets of bases we could use to describe this system. The first one is J1 M1 and J2 M2. This is the tensor product. So you could view it this way as well. It's the tensor product of the two degrees of freedom. So here, these kits are eigenkits, simultaneous eigenkits of J1 squared, J2 squared, J1z, and J2z, right? The other basis that we could pick are the eigenkits of J1 squared and J2 squared, as before, but now the total angular momentum and the total z component of the z component of the total angular momentum. So we wrote them this way. And then we mentioned that because in this notation, J1 and J2 repeat, sometimes express it. So these are two bases that describe the same Hilbert space. The Hilbert space is 2J1 plus 1 times 2J2 plus 1 dimensional. So there's a unitary that rotates these two, the bases into each other. So this is how we define it. So this is the base, the unitary that rotates the basis of the first basis, right? The tensor product one, to the second basis is going to be described by these matrix elements. These are called the Clebsch-Gordon coefficients. All I've done is I've inserted a resolution of identity in the middle. Good. Any questions? So these are Clebsch-Gordon coefficients. Sometimes I write CG coefficients. Gordon. I think. Yeah, I don't remember. Okay. So we said sometimes we use a simplified notation of M1, M2, Jm. The Clebsch-Gordon coefficients are real. This was convention. So if this is a unitary matrix and the matrix elements are real, the matrices are orthogonal. So the real unitary matrices are orthogonal, which means that they satisfy the matrix times its transpose as identity, that relation. Okay. There are a bunch of properties that were listed for Clebsch-Gordon coefficients. First thing was that the M1, M2, Jm, this is non-zero unless M1 plus M2 adds up to M. That's just a simple statement about the fact that Jz is J1z plus J2z. So if you recall, the way we proved it is that we looked at the matrix elements of this operator. This operator is 0 on the left, or I forget, on the right we acted with on Jm, and on the left with M1, M2, or the opposite. I don't recall how I did on the board, but that's basically the idea. That's how you prove it. We also said that these matrix elements vanish unless the total angular momentum as between the absolute value of J1 minus J2 and J1 plus J2. So today, when we go through the Schwinger model of oscillators, this becomes somewhat intuitive. Previously, we just discussed the plausibility, the sanity check that the dimensionality of the Hilbert spaces add up correctly if this holds. But today we're going to see actually some sort of physical page. I'll give you guys a physical way of thinking about this. All right, any questions? Then we said that the way we calculate the Clebsch-Gordan coefficients is through recursion relations. So the way the way the recursion relations were constructed was by inserting J plus and J minus, right? So similar to what I just wrote. So J1, J plus and J minus are the same as J1 plus J2 plus, that's J plus, and similarly for minus. So you insert the zero operator in the middle. On the left-hand side, you act with, for example, J plus on this ket, option B, and then the other terms you act on this bra, and you bring it to the right-hand side, you end up with this recursive relation. So this was a master relation we had, right? And when the upper sign has to do with J plus and the lower sign has to do with J minus. So we had this picture of way of visualizing this relation in the M1, M2 plane. So what I'm drawing here is the M1, M2 plane. This is M1 direction, this is M2 direction. And when you act with J plus, the left-hand side sits up here, and you relate this guy into these two terms, Clebsch-Gordan terms. Whereas when you apply J minus, this is the left-hand side, and you relate it to these two terms with the coefficients that we had up here. All right, any questions? So we use these relations as an example to find the Clebsch-Gordan coefficient for spin half particle for when J1, we took it to be the orbital angular momentum, and J2, we took it to be the spin angular momentum spin for the spin half particle. We did the calculation and we found that here's the matrix, the basis transformation. This basis is this is the first basis and this is the second basis, right? And here's the matrix that rotates it. Because it's real, it's a SO2 matrix, right? Orthogonal matrix that has determinant 1. So it's nothing but cosine beta, sine beta minus sine beta, cosine beta. And we use this to define this, what we call the spin angular functions, right? So these are the eigenkets of J1, in this case, L, S, J, and JZ, which is LZ plus SC. Okay, so this is a quick review of what we discussed last time. Are there any questions? Any thoughts? All right. So today what we're gonna do is I'm gonna first give you another way of thinking about addition of angular momentum or angular momentum due to Schwinger that relates this SU2 algebra we've been talking about to the algebra of simple harmonic oscillator, the creation annihilation operator, simple harmonic oscillator. And it simplifies certain calculations, and it's an important connection. So we'll not have time for me to explain the mathematics behind it, I guess a deeper level, to give you a deeper level understanding of it. Well, it's a certain statements about group theory, but so that's basically the idea. The idea is that you relate the algebra of two harmonic oscillators, so A and A dagger. So you have a pair of them, A plus and A plus dagger, A minus and A minus dagger, to the SU2 algebra. Here's the SU2 algebra. You have JZ, J plus minus, satisfy this, and I mentioned that this looks like a raising, similar to raising lowering operators. And the SU2 tells you that the commutator J plus and J minus is 2H bar JZ. So we'll go over this, and I will give you an example of how this could simplify things. And then I'll finish with a review of the whole discussion of angular momentum part of the course. So that's what the plan for the day is. So for this pair of harmonic oscillators, you have the number operator, right? N plus and A minus. This is a number operator for the plus sign is the number operator for the plus oscillator, and the minus sign is number operator for minus oscillator. They satisfy these relations. This is what it means to say that this is a lowering operator and this is a raising operator, because using this commutator, we saw that if you start with a state which was an eigenket of n, using this relation, you can show that A acting on that ket is a new eigenstate of n, with that's proportional to ket n minus 1. Similarly here, n plus 1. All right, is it clear what we're going to discuss, what the idea is? So this is going to be a rather straightforward connection between two different things that you've seen, right? Harmonic oscillator algebra and the angular momentum algebra. Any questions? Okay. So what are we talking about? We have two simple harmonic oscillators. There's a basis for that. So the ket n plus n minus. So just if there's something that you don't know about the notation, please do ask. So here is this means the state, right? There's a setup where you have n plus unit of energy, and for the plus oscillator, and n minus unit for the minus oscillator. So here are the eigenkets of n plus and n minus. When you act with A plus and A minus, this, interesting. Sorry, these are typos. So I should not, well, good that so when you do this, you're gonna get n plus minus 1 n minus, and when you act with A minus on n plus n minus, you're gonna get this. Are these two relations familiar? This is what we had for two simple harmonic oscillators. Let me fix this equation as well. So this is a raising operator. So this is how it acts. Oops. And I have to erase the minus sign. Right? So this raises n minus operator oscillator from n minus to n minus plus 1, and this is a coefficient that we found for it. Similarly here, right? So the vacuum state is the state that is killed by both a plus and a minus, right? You could also, as I said above, this you could think of as 0 of the plus oscillator tensor 0 minus oscillator. Then we saw that actually the ket n could be written, well, it's exactly these relations, as a plus dagger to the power of n plus, a minus to the power dagger to the power of n minus, and this is a normalization that follows from these relations. All right, is this representation clear? I just have two simple harmonic oscillators. And there is a pair of raising and lowering operators. They satisfy this algebra up here. Questions? Oops. Any questions about this? All right. So what is the goal? The goal is we are gonna relate this pair of harmonic oscillators and the Hilbert space representation of it and the algebra and all these kets to the algebra of angular momentum. So the SU2 algebra, rotations, right? That's the idea. Okay. What is the dictionary that goes between the two? Well, we have the creation and annihilation operators. Let me remind you how things worked. So n plus is a plus dagger a plus, and n minus is a minus dagger a minus, right? When you act with this first annihilates a unit of n minus, and then this puts it back, but you end up with an overall n, two square root n's that multiply it. Similarly here. Now j plus over h bar is something that looks like a number operator, but you lower an excitation from the left oscillator and you raise it in the plus oscillator. Similarly, this is the opposite process. So you could think of this in physics. Sometimes we call this the jump operator. An excitation jumps, in this case, from in this case, an excitation that jumps from minus to plus, and this from plus to minus. Oops. Good. So these operators, hopefully it's clear that this operator preserves the total number of excitations, which is n plus plus n minus. Because what it does is that it removes a unit of energy from minus oscillator and puts it in the plus oscillator, or vice versa. Now that we have defined these, so these are jump operators. We have a pair of other operators. One is the total excitation number, n plus minus n minus, plus and minus. And then we have the difference between the two. The difference between the two, h bar over 2, so h bar, just think of this divided by h bar, which is the difference between the n plus minus and minus over 2. This plays the role of the z component of angular momentum. Now, with these definitions, you could check explicitly that j plus j minus and jz, they satisfy this commutation relation. J plus and J minus satisfy this commutation relation. This is nothing but the SU2 algebra, or the algebra of angular momentum or spin, right? So it's the angular momentum or spin algebra. As I said, yeah, it's straightforward to see that the total number operator commutes with JZ and J plus minus. So J plus minus, I said that it's a jump operator. These are jump operators, so the total excitation number is conserved. And N and JZ they also commute because N plus and N minus commute. All right, any questions?
So yeah, I've got a question. So back when we looked at spin angular momentum, there were
Right.
also other operators defined as J plus and J minus, and they are equal to like JX plus I, JY. Should we be drawing a connection to that? There's these commutation relations that you
They
just
are
presented
exactly
show they're the same.
they're exactly the same. Yeah.
Okay.
So I just defined for you. Okay, so what I defined for you is the set of J1, J plus and J minus operators, right? Now use these relations to define Jx and Jy. We're going to do this in a bit. And then you realize that once you do that, J, I, J, J, they satisfy I, H bar, epsilon, I, J, K, J, K. These relations are equivalent to those.
Okay, makes sense.
Yeah. Any other questions? It is kind of interesting that basically at this point, all you know is the simple harmonic oscillator. That was the simplest example possible. And then the angular momentum one. And now we just related them, right? They're related. And you could think of angular momentum in terms of a pair of harmonic oscillators. Any other questions? I encourage you guys to think about this connection a little bit carefully. It's a deep connection. All right. So what is the J squared operator? So J squared is JZ squared plus JX squared plus JY squared. But based on these relations, you realize that JX squared plus JY squared is this combination. We used this identity many times in the past. Now we know what J plus and J minus are in our language, right? So these were the jump operators. You just plug them in and realize that the total spin operator, J squared, is H bar squared over 2n times n over 2 plus 1. Good. Now it's pretty straightforward to check that this operator also satisfies what you expect, which is it commutes with Jx, commutes with Jy, commutes with Jz. Right? It's in the center. All right. So how do we think of this? I'm gonna make another pause, before trying to give you a physical picture to think about this. A physical way of thinking about this. Are the algebraic relations clear? Okay. So n plus was the total number of excitation in the plus oscillator, and n minus is the total number of excitation in the minus oscillator. You could think of the spin up as 1 unit of plus type oscillator and spin down as 1 unit of plus down oscillator. Now Jz would be h bar over 2n plus minus n minus. This is the total number of spin up minus spin down. So I'm going to give you some physical pictures to think about actually, maybe in a bit. Maybe I can do it now. Let me see. Uh-oh. What failed? Recording failed? What happened? Anyway, I don't know what was going on. Yeah, let me go through these relations first, and then I give you the physical picture. All right. So with these definitions, how does J plus act? So the action of J plus, if you recall, was H bar, A plus dagger, A minus. Sorry. Yeah, that's right. A plus dagger, A minus, which gives you this coefficient. The square root of n plus 1, n plus plus 1 comes from A plus dagger, and this comes from A minus. Similarly, this is J minus, and here is JZ. So to go to the angular momentum, what we do is, as I said, we replace the sum of the average of n plus n minus over 2 by this is a quantum number, by the quantum number J, and n plus minus n minus over 2 with the quantum number M. When you do that, these coefficients, n minus times n plus 1 plus 1, it goes to this coefficient, and this one goes to this coefficient. Now, that should be familiar from using this change of variables. You realize that these relations are nothing but J plus Jm is J minus J plus minus 1 J m plus 1 and J minus. These are the SU2 relations we'd found before. So these are, after this change of variables, this is the equation. These equations become this, and these are familiar, hopefully, from the SU2 case when we work this out. Similarly, the eigenvalues of the J squared operator, this guy, which is n up to h bar squared, is n over 2 times n over 2 plus 1, goes to h bar squared J times J plus 1, as expected, right? So we find that the ket Jm written in Schwinger oscillator model is nothing but the vacuum, which is 0, 0, acted on with A plus dagger to the power of J plus M, A minus dagger to the power of J minus M. This is N plus over 2. This is N, actually not over 2. N plus, and then this is N minus. Good. So from this, it follows that the ket Jj is A plus dagger to the power of 2j over square root 2j factorial. So this 0 is the same state as this. It's the same state as this. So using this picture, you could see what is going on. What you have is a 2j. Think of this as this state, this ket jj. This is 2j spin half degrees of freedom. They're all pointing up. In this case, the total z component becomes j. Now the ket jm is still this 2j little spin degrees of freedom, where now j minus m of m are down and j plus m of m are up. Right? This is what I meant when I said n plus is the number of spin up and n minus is the number of spin down. Right? Because in this notation, you can see here, that J plus M is N plus and J minus M is N minus. Good. So let me pause here. Is this picture clear? Now this way of thinking about stuff, it looks like what we're adding is that we're adding 2J spin half particles. So we're constructing the kit JM from 2J spin half particles. M here tells you about how many extra ups do you have compared to, well, how many extra up minus down you have divided by 2. And when you consider such things, you can see that this could be J or J minus 1 or J minus 2, and so on and so forth. Good. So is the model Schwinger model for harmonic oscillator for Schwinger oscillator model of angular momentum clear? Okay. So we're gonna do a sample calculation. What is this sample calculation? We're gonna use the oscillator model of Schwinger to calculate the rotation matrices. In particular, what we're gonna calculate is the rotation matrix, representation of rotation by angle beta around axis Y. Why? Because we saw that when we were talking about the Euler angles, we wrote an arbitrary rotation as a rotation by angle alpha around Z component, by angle beta around Y component, and by angle gamma around Z component. Now the part that had to do with the rotations around Z components, once you plug in the representation theory of SU2, they come out as phases, and this is all that we had to calculate. And 2 examples in your homework, I kind of made you do explicit calculations of what these matrices, what the matrix elements of this rotation is. What we're gonna do is that we're gonna derive that using Schwinger oscillator model. Good. So the state that is J equals 0, M equals 0, sometimes called S wave. This is a state with no spin. It's rotation invariant. It corresponds to the ket in the oscillator model 0, 0. Right? Because this is the only way, because J is N plus plus and minus, and M is N plus minus and minus. If you want both of them to be 0, the only way for it is that N plus is 0 and minus is 0. So this is a vacuum. It's rotation invariant. What we're going to do is that we're going to calculate an arbitrary rotation of this vector. All right, so what does that look like? Well, this is going to be d of r acting on Jm. What is Jm? If you recall, Jm is a plus dagger to the power of J plus m, a minus dagger to the power of J minus m, with these coefficients down here in the denominator, acting on 0 and 0. I have d of r on the left, so just insert d dagger of r and d of r here, they cancel out. Is that clear? Is it clear what I've done? Let me do this a little bit more slowly. So this is 0, 0. because this is invariant under rotations, I can always add, I can always act with it with this. The state is invariant under this, so 0, 0 is equal to this. Then I have this guy to the power of j minus m. So think of this inserted j minus m times. And in between each of these guys, I'm going to insert d minus 1d, d minus 1d, d minus 1d. That will could be repackaged in this form. Then similarly, I have a plus dagger, j plus m of m, and by inserting d minus 1d in between them, you're going to get this expression. This last guy comes from this last term. So is this expression clear? Okay. All we need to do is we need to calculate these rotation matrices, these rotations. How do we do that? We use the Baker-Campbell-Hausdorff, right? So if you have Baker-Campbell-Hausdorff, your d of r of beta, we're considering rotation around the axis beta, axis y by angle beta. So here are what the rotations are. jy, a plus minus dagger in between. Using Baker BCH, you write it as this term plus minus I beta over h bar, the commutator plus this guy squared half the nested commutator, right? This was the BCH. All we need to compute is that we need to compute this term, and see if there's a structure that allows us to resum all these terms. Good. All right, so let's do the calculation. What is jy? We just mentioned this earlier. Jy is just 1 over 2i j plus minus j minus. This is just a consequence of the fact that j plus minus is jx plus minus I jy. Right? So what we have is minus jy over h bar. There are a bunch of I betas outside. So let's calculate the first term. The first term is j plus and j minus are these jumping operators, these hopping operators. I think, yeah, jump or hop operators. And this is the commutator. You just use the properties of commutation relations and the fact that the commutator is central. Hopefully you recall that. You end up with the fact that the first order commutator is 1 over 2i a minus dag. Good. So if you want to calculate now the second order term, you have to calculate the nested commutator this way. We just calculated this commutator. It was a minus dagger over 2i. Repeating that calculation, it becomes 1 over 4 a plus dagger. Now that you got a plus dagger, the third order term, you recycle this calculation. The fourth order term, you recycle this calculation. So all the even and all the odd terms could be recast in terms of the following two relations. This is what happens to a plus dagger under rotation on the y-axis by angle beta. That's not surprising that you find what this is. It's just a rotation matrix of this form. We had already seen this, right? The half has to do with the fact that this is spin half. Good. Now we have these relations. Look at this. All I need to do is we just calculated what these two terms are. in this form, we need to plug in these two terms inside these parentheses and take them to the power of j plus m and j minus m. The result is going to be this. So the first term is this guy to the power of j plus m. The second term is this guy to the power of j minus m. There's something called the binomial expansion. This is a very important fundamental concept in probability theory and physics. What it is that if you have x plus y is to the power of n, this is a series expansion of x plus y to the power of n. Here what you have is the sum of two terms to the power of j plus m, sum of two terms to the power of j minus m. So you could use this power expansion of objects like this. Once you expand this, it's going to be a homework problem, but you work it out and you learn that dr of b, rotation around the y-axis by angle beta acting on jm, becomes this longer expression like this. Questions?
So essentially this method provides a kind of more tractable way to actually get a matrix for
Yeah,
the representations of rotations, right?
exactly. We're going to do that. We're going to write down a master equation in a second. We already have all the ingredients.
Okay.
Any other questions? Okay. So as we just talked about, we discussed just right now what we're after in to understand how an arbitrary rotation acts on a spin degree of freedom. We need these matrix elements, right? That are labeled by the, so m prime m are the matrix elements and j is the spin j, right? And beta is the angle. To find these matrix elements, well, we just did find them. That's it. You just take the state and write it this way, and you find that these matrix elements could be written explicitly in the form this. So you had a homework problem where you were trying to solve for spin 1 example of this. I think it also asked you guys to do the spin 2 calculation, see how much harder it gets as we go. But here's a closed form expression for it that we just derived using the Schwinger oscillator model. Schwinger oscillator model is a very simple story, but I think it takes some getting used to. Any questions? What I'm gonna do in the remaining half an hour or so is just I'm gonna summarize everything we've discussed, do a quick and high-level summary of everything we've discussed about angular momentum and addition of angular momentum. But it's a good moment to pause and think if you have any questions. It's a good time to ask. Okay. The summary of part 4, quantum angular momentum. We said that particles in quantum mechanics can have an intrinsic property, actually do have an intrinsic property called spin, or spin angular momentum. This is a property besides the regular orbital angular momentum. So orbital angular momentum is the thing that's like r plus p, but spin angular momentum is some abstract concept. It's that it's a property, it's an abstract quantum property of the particle. And for example, when you talk about putting the system in some background magnetic field, both of them respond, right? The spin will rotate, and so will the wave function spatial part of the Hilbert space. So the total Hilbert space in this case is the Hilbert space that has to do with the spatial part of the wave function, tensor the Hilbert space of the spin part of the wave function. We saw, for example, if you have spin j, this Hilbert space is 2j plus 1 dimensional. But if you have a free particle, this Hilbert space is infinite dimensional. right? So the action of a rotation would correspond to a representation of rotation on the orbital part, tensor, representation of rotation in the spin part, right? And this notation means around the ket and hat by angle phi. We saw already that this is how we represent this. Good. We discussed Euler angles. Euler angles were set up where we describe it an arbitrary rotation in terms of rotations around fixed axes, z, y, z. That was the fact that z, y, z and not another combination is convention. So the spin representation was the following algebra. So Jj satisfy the SU2 algebra. There is a pair of operators, j squared and jz, that commute, and the j squared commutes with all the ji's. Here are the eigenkets, the simultaneous eigenkets. We use them as we use the notation of ket jm. We saw that m runs from minus j to j, and then j has to take values of half integer, 0, half, 1, 3 halves, 2, blah, blah, blah. Right? If this is spin, this is how it works. If it's orbital angular momentum, it cannot take half integer values. It has to take integer values, positive integer values. In orbital angular momentum, as I just said, here are the commutation relations. They're exactly identical. You describe them using 2L plus 1 dimensional Hilbert space. L and M are the simultaneous eigenket of L squared and LZ. But now the only difference is that, M runs from minus L to L. This was the same as before, but L cannot take half integer values. And the reason was that the wave function in the spatial part of the wave function has to be single valued under rotation by 2 pi. Good. Then we discussed the addition of angular momentum. When we talked about the addition of angular momentum, here's how we represented things. We had two bases, the basis of the total spin or angular momentum. These are the eigenkets of these operators, and then the second option is basically eigenkets of the individual system tensored, right? We saw that there are these unitaries that take us in between the two frames. The matrix elements of those unitaries are called Clebsch-Gordon coefficient. We said that the Clebsch-Gordon coefficients are real, and which means that they were actually orthogonal matrices. Good. So, and then today, what we did was we redid this whole representation theory of SU2 for spin using the two simple harmonic oscillators A plus and A minus, right? So the master equations were these relations, right? So we defined the jump operators using and then JZ was the difference between the total number operator. The total number operator is N. This jump operators, they satisfy the right relations as you expect from SU2 this way, and then the total spin is basically N over 2 times N over 2 plus 1. All right, are there any questions? Today was a shorter lecture. It's the Thanksgiving week. But we've reached the end of the part 4 of the course, and what remains is we have only 2 more lectures left. Those 2 lectures are going to be about formal discussion of symmetry in quantum mechanics. So you've seen various manifestations of symmetry. We talked about translation symmetry in time and space, which led to the definitions for generator of spatial translations for momenta. generator of time translations were Hamiltonian. Hamiltonian gave us dynamics. Momentum, we saw that it led to the construction of the Hilbert space of a free particle. We talked about the angular momentum, or spin. These have to do with rotation, transformation of things under rotation. So it's a form of symmetry. So then we're gonna just spend 2 lectures talking about the role of symmetry in quantum mechanics. All right, are there any last questions?
I just had a question about the final exam.
Yeah,
So is it gonna be open notes, or will it just be no notes allowed?
no notes, but let's say textbook.
So the textbook will be allowed in the exam?
The textbook is allowed, yeah, Sakurai.
Okay, thank you.
Sure. Any other questions? All right, did I have any other announcements? I did say that there is an extra problem solving session that I'm gonna host. I'm gonna run on the last lecture, which is December 7, I believe, but they'll do double check. The final exam is on December 10, I believe, in the afternoon. I might be getting the time wrong. I thought it's 3:30 or something. Do check. Yeah, that's it basically. And I talked to all the TAs, and they promised to that they're going to try to grade as much as they can by the exam. All right. Any last